So we got started on titanium, and we essentially went through the slip and twin systems for the HCP alpha phase, and we looked at the high temperature beta phase, the slip systems that are available there. And we can sort of, just like we did with steel, link different compositions to different phase diagram behavior. So if we have normally we would have the transformation from alpha to beta would just happen at the beta solvus temperature, and zirconium, which is also a group 4 metal, and tin are essentially neutral on that transformation, right? And so we have a transformation a phase diagram that looks like the pure metal. If we have alpha stabilizers, we develop a two-phase region, right? An alpha plus beta mixed phase field, and the most common alpha stabilizers are, right, aluminum, which is in solid state solution, and then oxygen, nitrogen, and carbon, which are, of course, interstitial, right? So interstitials are strong alpha stabilizers, which is the opposite of what we saw in steel, right? The interstitials were strong austenite stabilizers, right? And so they, in steel, interstitial stabilize the high temperature phase, and titanium, they stabilize the low temperature hexagonal phase. Right? The common beta stabilizers we break into two general categories: isomorphous or eutectoid, depending on the effect on the phase diagram and where the two-phase, how far down the two-phase field extends, right, before you create other compounds, right? And so really it's the same behavior. It's just, where does this line, right? If the eutectoid point is lower than room temperature, right? And so vanadium, molybdenum, niobium, tantalum are the common ones here, right? And iron, manganese, chrome, nickel, copper, silicon. H? Oh, hydrogen. I've never paid any attention to that. And I think, of course, hydrogen is going to go interstitial as well, right? This is essentially the same information, just on a slightly different presentation, right? And we can see, adding aluminum, right, you get a wealth of intermetallic phases, titanium aluminides, right, that really complicate things, right? So most of the systems of interest, right, get really, really complicated really quickly, right? In these right. So it's a little hard to a little hard to see, but we've got, is that omega there or is that alpha 2? That's alpha 2. Yeah. So omega doesn't appear on here. You get other phases like this delta phase. Right? So most of the time you can imagine that we're aluminum as an alpha stabilizer. We're going to be down here at relatively small weight percents.
What is sulfur 2?
We'll get to those.
Center you written alpha plus alpha 2, but this side it is alpha 3. Right? If that field is alpha plus alpha 2.
Where do we see? So this here is, where's the cursor? This is alpha.
Alpha plus alpha 2, right?
Yeah.
The next thing should be alpha 2,
It's just a blurry phase diagram. I think it is alpha 2. Right. But anyway, the point is things are messy, right? Right. So if you go back to that chart where he says where we at the very beginning, right here, where I pointed out how many different possible alloying elements there are, right? This doesn't talk about the range of solid solutions that they can exist in. Some of these have fairly limited solubilities, right? So low amounts of alloying, right? But you have a wide degree of choices, but not necessarily a large solubility. Right. Okay. Right. And again, this is sort of the same type of information, just sort of presented in different ways. Right. So the alpha prime, alpha 2, alpha double prime, these are all martensitic phases, right? Depending on the cooling rate from beta, you can develop those. Omega phase is simple hexagonal, right? And so we'll talk about these reactions coming up. Okay, so generally we're going to classify our tie alloys as either alpha, near alpha, alpha plus beta. These are the commercially most important group, and the beta alloys. And so if we look at general property trends for each of these, generally the increase, as we go from pure alpha, as we increase beta, we generally improve our strength in intermediate temperature range and low and intermediate temperature, our machinability and fabricability and ductility, right? And as we add more alpha, we improve our creep strength and weldability of our alloys, right? And so generally things like 6.4 are down here, right? Because it has reasonably good creep strength, and you can weld it, right? So as you get over into the beta alloys, you lose your creep strength. Okay, so pure alpha alloys. Again, there's a lot of repeated information here. Our alpha, we're just relisting the alpha and beta stabilizers, neutral elements. So if we have a pure alpha alloy, we're generally going to rely on solid solution strengthening. Grain size refinement, we have a reasonable Hall-Petch slope, cold work, and sometimes you can get some martensitic reactions, but it's not. There's no commercial benefit to it because it's not heat treatable. As soon as you give it any temperature, you transform from the martensitic phases to regular alpha, and so you can't get a lot of strengthening. These are primarily used for corrosion resistance, right? Remember, you get a coherent titanium oxide passivating film, right? And so pure alpha alloys are used a lot for chemistry, heat exchangers, and cladding type applications, right? There was just a big ARPA-E call for new ways of manufacturing heat exchangers to take advantage of additive and things like this for alpha and near alpha alloys. So it's a kind of exciting technological area. What is important to note here is if you look at the effect of the interstitial content, right, the carbon, oxygen, and nitrogen on the strength, the effect on the strength, they have very high, they're very potent strengtheners, but also you lose ductility very, very quickly, right? And so you can look at your if you look at your change in oxygen from 0.18 weight percent to 0.25 weight percent, right, your yield strength goes from 170 to 275 megapascals, right? But you're also going to suffer a huge amount of loss of ductility, right? And you're still nowhere near the strength of, say, the yield strength of, say, Ti 6.4, which is 870, right? So the alpha alloys, even in their strengthened state, are still significantly weaker than the commercially important alpha plus beta alloys. So that's where we're going to spend a bit of time today. And we have a lot of opportunity to tweak our microstructure and really go after properties in the alpha plus beta. Primarily, we're messing around with the beta to beta plus alpha transformation, but we also have other phases that can form, right? We have our martensitic phases, our omega phase, and beta 1 and beta 2, which are both BCC, but they both have different compositions than the beta phase, and they also have a different lattice parameter. So there's a strain effects associated with they're spinodal or quasi-spinodal type phases. Right. What's that?
What kind of things will lead to omega?
We'll talk about all these different reactions, right? And so again, with steel, we're really looking at exploiting these combinations of phase transformations to optimize our mechanical properties, right? There's a huge amount of space that we can play from. And so if we look at a sort of a typical regime, we'll call this beta processed titanium, where we cool from a beta solutionized state. There's my pointer. I've lost it. There we are. Okay. So we cool, we solutionize, we cool down, then we come back up into the two-phase region, we cool back down, and then we give it a stabilization treatment. So when we cool down quickly from the solutionized state, we get formation of allotropomorphic grain boundary alpha that are on the prior beta grain boundaries, and will begin to form some Widmanstätten alpha, right? So completely analogous to steel in this case, right? Will grow. Right? So then when we heat back up into the two-phase region, right, the alpha plus beta anneal or the alpha plus beta hold, right, we will partially dissolve the Widmanstätten plates and will thicken these the alpha ribs. We'll cool down and we'll thicken our alpha plates, and so now we have little beta ribs in between here, this dark phase, and then we form very fine secondary alpha in the beta ribs, right? And then the stabilization treatment here, much lower in the two-phase region, essentially just allows the formation of very fine secondary alpha in the remaining beta phase, and we come to essentially equilibrium phase fractions in chemistry for this temperature. Right? And so depending on the cooling rate, we can change our structure quite a bit. So here we see what is typically called a colony microstructure. So these regions are one variant of alpha, right? There are multiple variants that can form, just like there were multiple Martensite variants that can form, multiple bainite variants that can form. Here we have multiple alpha variants that have a fixed orientation relationship with the beta. So they come in clusters, a colony of alpha LAS that all are of the same variant. Here we see our allotropomorphic alpha on the grain boundary, right? And we get structures like this at generally slower cooling rates, right? If we cool a little faster, we get what's colloquially known as a basket weave structure, right? Where we nucleate multiple variants in a small spatial, right? As we cool down, our driving force for nucleation increases, so we nucleate a lot more variants, and we get these intersecting structures, right? And I had mentioned secondary alpha before, so you can see the length scale on this. This is 2 microns, right? And here's the secondary alpha in the remaining beta matrix, right? Remember, we're holding this in the two-phase alpha plus beta phase field, right? So, yeah.
Will come from the solutionizing temperature or alpha plus beta?
The alpha plus beta.
Secondary alpha.
Right. So this is going to be cooling from the pure beta phase field, from the solutionizing field, right? Because you're going to grow your Widmanstätten laths on cooling, right? So I would say the skeleton of your structure is formed there. Then when you take it back up into the two-phase field, you're dissolving some of the Widmanstatin and growing the alpha laths that are there, right? And so these secondary laths are much, much more refined compared to the primary alpha laths. They really play a very important role in the strengthening, right? You can imagine, right? These are very potent obstacles to any slip you would have in the BCC structure, right? So that means you're pretty much going to be strongly limited by the amount of slip you can accommodate in these alpha plates, right? And especially if you have a basket weave structure where you've got multiple different directions that need to be accommodated. Here's some EBSD I did not too long ago. This was TKD. This was pretty impressed. I did this with John Horsborn. This is one of the first TKD data sets that we did here. So super proud about that. This was a TEM foil that we didn't have a proper sample holder, so we just used some carbon tape and stuck it to the edge of a razor blade, and then mounted the razor blade in the SEM. So, for those of you who don't know, transmission kikuchi is just like EBSD, except you hold a TEM foil up near the pole piece in the SEM, and the diffraction happens forward scatter rather than back scatter. So you're doing transmission imaging in the scanning electron microscope. But you can see the large number of variants of the secondary alpha that forms, right? In this length scale, this is 500 nanometers, right? So these are pretty dang thin. These are like 50 nanometer thin features, right? So kind of a question to ponder, right? So here, these are unfortunately at different magnifications, right? But sort of think through what is going to affect the coarseness and the density of the secondary alpha, right? What thermal processing can you do to affect that, right? So just something to think about, right? Another common avenue is what is called alpha plus beta process, and this is basically the same idea, except on this hold in the alpha plus beta field, you're going to work it, either forge it or roll it, right? And so, again, cooling from beta is going to give you your allotropomorphic grain boundary alpha, Widmanstatin plates. We take it up high, a little bit higher typically into the alpha plus beta phase field than for beta processed, and then mechanically work it, and that develops these equiaxed globular alpha grains. And the mechanism by which this occurs is still not really understood, right? So it's either recrystallization, or my personal opinion is it's spheritization caused by extreme shearing of the alpha laths that then form a new grain, and then essentially the cooling from here develops the colony or basket weave structure, just as cooling from in the beta processed, and then the stabilization treatment is held. So if we look at the common features of alpha plus beta alloys, right? If you look at Ti-6-4 or Ti-17, right? These tend to be, depending on the condition, what you have, right? And so we're really looking at tweaking the prior beta grain boundary sizes, right? So what's our initial grain boundary structure that we're starting with, right? The cooling is going to determine how much grain boundary alpha that we can form. Also, whether we get colony or basket weave type structures, the amount of work, how much globular or equiax alpha that we have, what's the fraction between that and transformed beta grains, and then the amount of secondary alpha, right? So we have a huge amount of pure processing knobs that we can tweak. And I think if you ask anyone who really works in titanium, they'll say that the space has not been explored nearly as well as it should be, right? So we look at some of the other phases that we can form. The equilibrium phases is our beta and alpha, but as we mentioned, we have two martensitic phase, simple hexagonal omega phase, and beta 1 and beta 2. So if we look sort of at a schematic phase diagram, when we see where these metastable phases lie, right, as we increase our fraction of beta stabilizers, right, this now gives us a whole bunch of other knobs to turn, right? And so that's just sort of listing the reactions out, and we'll talk about them in more detail. So if we just look at beta transforming into beta plus alpha in the two-phase field, right, we get grain boundary alpha precipitates, and then Widmanstätten type laths growing from these grain boundary alpha precipitates. Depending on the range, these may coarsen into a full allotropomorphic grain boundary alpha layer, right? Or they'll coarsen to form this continuous grain boundary layer, right? So you see structures that look like this at the grain boundaries. So titanium is, one nice thing about it is there's this Berger's orientation relationship between the prior beta and the new alpha. And unlike steel, this holds exactly, right? So I didn't talk about it when I was doing steels, but one of my research projects is reconstructing the prior austenite grain structure from Martensite. And that's a difficult problem. And I'm by far not the only one that's doing it. I know of 6 other research groups around the world that are working on doing that same problem. Yeah. Yes. So this was the point I was going to make. It's very challenging in steels because there isn't a fixed orientation relationship, right? It's somewhere between Kurgemov, Sachs, and Nishiyama-Wasserman, and it's not constant anywhere, and the martensitic transformation is accompanied by plastic deformation. In titanium, this problem was actually solved quite some time ago because this Berger's orientation relationship is always observed and it's always dead on, right? There's no variability there's no variability in it. And basically you can see the relationship between the 1,1,0 plane in the BCC beta and the small amount of motion that needs to happen to make this be the basal plane in hexagonal, right? It's not super hard to visualize, and the 1,1,1 direction ends up being parallel with the 1,1 bar 2,0 direction, right? And this orientation relationship is observed within a degree or so across the entire image. So you can go through the crystallography, and that gives you 6 possible variants. Compare that to 24 in Martensite, right? So you are dealing with it's a lot less ill-posed going back, right? You have many fewer choices of what gets grouped together. All right. Or I should say 12 variants. You have 6 011 planes in BCC and 2 possible arrangements for 1,1 bar 2,0 to 1,1,1 directions. So we have half the number of variants that you do for steel, right? So essentially, this just shows the 2 variants that are on this, the same 1,1,0 pole relationships that are possible, right? And see, we talked about this in twinning and other Widmanstatten relationships. We get the same type of ledge terrace structure, right? Where these laths are lenticular for the most part, right? So how do they maintain that orientation relationship? Right. And essentially we get the same thing. We get steps that maintain it, followed by little terraces that maintain the orientation relationship, little steps where it deviates, and then growth happens by the motion of these highly mobile, high energy boundaries across to grow the alpha laths, right? So you can see now that we've done aluminum and steel, right? You've got the toolbox, right? We can move much faster through these concepts, right? And this was work that was done here at CMAS. Some of the first high-resolution TEM images that were done out of Professor Fraser's group, right? And so here you can see the atomic columns. This is the alpha, and this is beta. You can see the six-fold symmetry. And essentially here we have our ledges that perfectly obey, our terraces that perfectly obey the Berger's orientation relationship, and our general steps, which can then grow, right? So these steps are only a couple atomic units long, right? Or high, and about 6 or so kind of long, right? And so that's how we get our arbitrarily these lenticular laths. This is like absolutely amazing, right? I mean, if you think about it, it's really only been in the last 10 or so years that we've been able to actually see these postulated mechanisms, right? The actual structure of these. So, the characterization that we can do now is just completely mind-blowing. Were you going to say? Ask something? Or say something? Oh. Okay. So that's the equilibrium diffusional transformation, right? If we cool quickly, we don't have time, so we'll go to beta plus alpha prime Martensite. There's actually 3 known Martensite structures, right? And again, in right, the first one is this alpha prime martensitic phase, which is also hexagonal, and depending on composition, with increased solute content, you can either get lath martensite or slipped martensite, same as in steel, or you can get this lenticular or twin martensite. Right? Exactly the same analogy as increasing carbon content in the formation of steel martensite. As you increase your solute content, you get other phases. You can either get this alpha double prime, which is orthorhombic, or this alpha triple prime, which is also orthorhombic. Right. So the hexagonal is alpha prime hexagonal is the most common. Again, dilute alloys, right? And this does maintain the Berger's orientation relationship, right? Alpha double prime and alpha triple prime are almost always going to be twinned, internally twinned microstructures. And then, of course, you're going to have some metastable beta that remains, depending on the cooling rate. If you cool quickly enough and you can't actually transform everything. And this is going to be BCC, but it's going to typically have omega phase, fine dispersions of omega in it. Yeah.
There that you said that using solute, that element that you said, for example, in the beginning of this chapter.
Yeah, so molybdenum is one, so beta stabilizer, right? So, molybdenum example, right? And so this is just, again, some micrographs. And because it is martensite, right, it's athermal, it's diffusionless, there is no composition change, right? So all the analogies from steel hold over, right? Of course, then we can also temper, right? So on tempering, we're going to transform to our equilibrium product. So we're going to go from beta plus alpha prime to beta plus alpha, right? So the alpha prime is going to transform to alpha of equilibrium composition, which means we need to potentially partition elements, right? So we have to diffuse these out. Beta, right? The beta stabilizers are going to partition out, and we're going to form beta as fine precipitates at the boundaries between the alpha laths, right? And this for beta isomorphous alloys, right? If we have a eutectoid alloy, remember the eutectoid structure, right? So the eutectoid structure here, we're going to temper, and instead of diffusing out and forming beta, we're going to form intermetallics. Right. And you saw how convoluted some of the phase diagrams are. And we can have multiple different intermetallic forms. All right. So the alpha double prime Martensite, right, typically occurs with the Martensite start is typically very high temperature in these, right? And we end up with because the temperature is still relatively high, we have sort of auto-tempering that happens. We end up with a fine distribution of alpha within a matrix of alpha double prime lads, which on tempering, these will then coarsen into coarsening of these alpha precipitates, and then we'll have reactions at the prior beta grain boundaries to form a lamella alpha plus beta. Right. So if the Martensite start is at high temperatures, if the Martensite start for a particular alloy is at a lower temperature, this is much less common. Then you get alpha prime will transform to beta on tempering. Then the beta will decompose into alpha plus beta by a diffusional transformation. Right. But this is not as common of an occurrence. Okay. So omega phase is pretty much typically a detrimental phase. Right? It's going to form in alloys with a reasonable amount, a relatively large amount of beta stabilizer. Okay? The big disadvantage is its present leads to brittleness. It's really bad for your fatigue and fracture life if you have omega. However, it can be a potent nucleation site for alpha, right? So heterogeneous nucleation of alpha on the omega interface, right? So this can be occur to grow either athermally by quenching from the beta phase field, much like a martensitic type reaction, or isothermally by prolonged aging in this metastable beta plus omega phase field. Right? It's not HCP. It's hexagonal, but it's essentially it's simple hexagonal. Right? So if you think a simple cubic where you've got atoms just at the corners of your cell, here you've got your 6 atoms in your basal plane, and then your next basal layer is just stacked right on top of that. Right? So your unit cell is essentially 2 atoms, two layers thick. Right? Okay? And this is like Professor Fraser's like pet research area. And so when I took over this course last year, he gave me his notes, and there was honestly 40 slides on the transformation from beta to omega with all these movies. It was pretty great stuff, but it was just way too in-depth, looking at different mechanisms and which planes collapse in which order, and right. But basically, right, if we think about the BCC beta, we've got this ABC stacking sequence, and we get the 0th and the 3rd planes remain undisturbed. I liked Professor Fraser used the words undisplaced, which I thought was a very British way of saying it, so I kind of left it. Right, but these other planes, right, move, and you can see the going from the BCC. You can envision going to here a hexagonal hexagonal structure, right? And this is just some more. I couldn't bring myself to take all of it out, but here we see omega precipitation in a titanium 10% vanadium structure, right? And right, you can see these omega precipitates tend to be fairly fine, fine precipitates, right? And lots of TEM images going back, right? But depending on the exact composition, they can either be, and the misfit resulting from composition changes, right? They can either be ellipsoidal or cuboidal type precipitates. So again, it's really going to depend on the misfit between the lattice parameters of the omega and beta phases, right? Which depends on which alloying elements that you have in there, right? And we'll see this again. The larger misfits, you're going to have a cuboidal structure, and a small misfit, more circular or ellipsoidal. This will come up again in nickel superalloys. So why would a large misfit give you cuboidal? Right? This is something that always seems to a couple people always get this wrong on the nickel part of the exam. So I want to, right? Because you would think if there's a large misfit, what's your interfacial energy? High or low? High, right? So how do you, generally when you have a high interfacial energy, what do you do to reduce the energy of your system, right? You want to reduce your interfacial area, right? What is the shape that gives you the lowest surface area for a given volume? A sphere, right? So that line of logic will take you down that a high misfit will give you spheroidal particles, right? And that would be 100% true if these were isotropic, except we're dealing in a crystal, right? So different planes, right, will have the energy will be greater or lower on different interfaces, right? So by making your 8 low energy interfaces, we'll talk about like what those are in nickel, right? You can reduce your energy over by going spherical, right? So it seems counterintuitive at first unless you think about it being in a crystal and dealing with the anisotropy of directions in the crystal and the anisotropy and interface structure due to those crystallographic directions.
So what was the reason I didn't understand? Because
it's just the anisotropy of the crystal, right? So you can have planes that are lower in energy than others, right? So you will tend to grow to maximize the amount on those planes, right? So essentially, if you have a cuboidal particle, right, you can think about this being on the cube faces of the BCC, right, are going to be a much lower energy than other planes. Okay, so just to wrap up the omega stuff, right? So essentially, these omega precipitates can be very potent nucleation sites for alpha, right? This is titanium 10, vanadium 2, iron 3, aluminum, right? We get fine omega And then here again, TEM images. It's hard to see on the screen, but you can, here's a little easier, a high-res TEM. Here's omega. You can see alpha nucleating at this omega interface and growing into the surrounding beta, right?